Hi students, have a nice day. In this section we are going to discuss about the aromatic hydrocarbons. Aromatic hydrocarbons are also known as arenes. Okay, aromatic hydrocarbons are also known as arenes. The aromatic compound which contains benzene as a ring. Okay, benzene ring, it is called benzoids. Okay, aromatic hydrocarbons. Aromatic hydrocarbons. They are also known as arenes. Aroma means fragrance. That's why the name is obtained. Okay, aroma means sweet smell or sweet fragrance. So the compound which contains benzene ring, the compound which contains benzene ring are called benzoids. Benzoids. And the aromatic compound which do not contain benzene ring, not benzene ring is present. Okay, in the compound there is no benzene ring and the compound is aromatic, they are called non-benzoid. For example, furan. Okay, furan. Furan is an aromatic compound, but it comes under non-benzoid. Okay, another compound is naphthalene. It is a benzoid. Two benzene rings are fused. Two benzene rings are joined. So what are benzoids? Benzoids, the aromatic compounds, contains benzene ring. Non-benzoid means the aromatic compound do not contains benzene ring. So there is a two type of aromatic compounds, benzoid and non-benzoid. Okay, let's discuss some benzoids, their nomenclature, isomerism, etc. Okay, so benzene and its derivatives, benzoids, the compounds do not contain benzene ring are called non-benzoids. Yes, first is benzene itself. The first compound is benzene. Second, this one is benzene. The second compound is two benzene rings are fused. Two benzene rings are joined. So we get naphthalene. Naphthalene. It is used as a mothball, okay, and repellent compounds. Moths are away from the area where which this kept. And when three benzene rings are joined, it is called anthracene. Okay, or you can draw like this: three benzene rings. The molecular orbital structure can be used in some textbook. It is drawn like this: dotted circles. Okay, so this is called anthracene. Anthracene, and the position is changed. One benzene ring is attached in the sidewise, or the compound is like this. It is called a phenanthracene. Okay, sorry. It is called a phenanthracene. Phenanthracene. Okay. One benzene ring, two benzene ring, it is naphthalene. Three benzene ring, it is anthracene. It's isomer. Okay, phenanthracene. The next we discuss substituted benzene. Substituted benzene. Alkyl groups or phenyl groups is substituted in the benzene ring If the methyl group is substituted, you know that it is toluene. Okay, the methyl group substituted, the compound is toluene. Okay, let's discuss the compound. Benzene ring and methyl group is attached. You can draw circular alternate double bond, it is toluene. Toluene. And if the ethyl group is attached, CH2, CH3. The IUPAC name is methyl benzene. Methyl benzene. Here the IUPAC name is ethyl benzene. Okay, ethyl benzene. Then if two methyl group is substituted, CH3, the compound is silane. Okay, it is orthosilane. Orthosilane. What is its IUPAC name? 1,2-dimethyl benzene. 1,2-dimethyl benzene. Okay, and it has a position isomer. The methyl group changes its position 1,3, and you know that 1,3 position is meta position. So what is the name of the compound? Metasilane. Metasilane. IUPAC name 1,3 dimethyl benzene. Dimethyl benzene. And these two are position isomers. Nomenclature as well as isomerism. Okay. These two are isomers. Okay. But not position isomers. These two are isomers. The formula, you can check it. Okay. These two are isomers but not position isomers. 1,2 dimethyl benzene and 1,3 dimethyl benzene are position isomers. One more position isomer is there. Which one? Okay, methyl benzene I erase. One more position isomer. What is it? The methyl group on the 1,4 position. 1, 2, 3, 4. It is parasilane. Okay, it is parasilane. Then its IUPAC name is 1,4 dimethyl benzene. Okay, dimethyl benzene. Okay, so that's about the naming and isomerism. Naming of aromatic compound is easy. Okay, already we discussed the naming of the aromatic compound. Benzene, one methyl group comes toluene, then ethyl group comes ethyl benzene, then two methyl group comes, they are called silanes. Silanes have position isomers, orthosilane or 1,2-dimethyl benzene, metasilane or 1,3-dimethyl benzene, parasilane or 1,4-dimethyl benzene. Okay, and remember that these three are orthosilane, metasilane and parasilane are position isomers. These two are isomers but not position isomers. We can say it is structural isomerism, chain isomerism. Chain is different. Here is ethyl group, so in this case 2-methyl group. Okay, next we discuss the structure of benzene. Michael Faraday isolated benzene in 1825, and the formula of the benzene is C6H5. From this formula, they understand that the benzene is highly unsaturated, and also the evidence from some reactions. Benzene form triozonide, and that's why the scientist assumed it contains 3 double bonds. Okay, benzene form triosonide, and that's why benzene contains 3 double bonds. And also benzene form mono-substituted derivatives. It reveals that the 6 carbon are identical. Okay, once again, benzene form mono derivative compounds. It reveals that the 6 carbon atoms are identical. And from the formula, it is clear that the 6 carbon and the 6 hydrogens are identical. Okay, C6H6. The formula is C6H6. In 1865, okay, Kegel, a scientist, proposed the structure of benzene by drawing alternate double bonds. Okay, the possible structure of benzene is 6 carbon atom. Okay, 6 carbon atom and 6 hydrogen atoms. 6 carbon atom and 6 hydrogen atom. And the tetravalency is maintained by putting alternate double bonds. And it is condensed into this formula. Okay, so 6 carbon atoms. All these coordinates are carbon atoms. You remember that. And 6 hydrogen atoms. So 6 carbon and 6 hydrogen. To make a tetravalency, Kegel put alternate double bonds, and that is a structure. Another possibility, this is structure 1. Another possibility, the position of double bond change is structure 2. The double bond is like this. So let's number the carbon atom in order to distinguish. Let's number the carbon atom 1, 2, 3, 4, 5, 6. Here also 1, 2, 3, 4, 5, 6. And the chemical studies, 1, 2 dibromobenzene, Br. Okay, 1, 2 dibromobenzene has 2 possible structures. First one is this one, and the second one is Br, then the bond is like this. So 2 possibilities. In the first possibility, 2 bromine atom is attached to the doubly bonded carbon atom. Okay, the double bond between the carbon atoms in which the bromine are attached. Then this is the 2 bromines attached to carbon atom, they are joined by a single bond. So 2 possible structures proposed by Kegel. Okay, the scientist Kegel. Some teachers pronounce it Kegule. Kegel is the correct one. Okay, so these are the 2 possibilities of structure of benzene. But the problem is that there is no evidence. Okay, the evidence of single bond and a double bond did not proved by the experimentation. X-ray diffraction study shows that the benzene, the 6 carbon are joined by a similar type of bond, because in carbon-carbon single bond, the carbon-carbon single bond, the length is 154 picometer. 154 picometer. And carbon-carbon double bond, the bond length is 132 picometer. And in benzene, now 154 picometer and also 132 picometer. There is no evidence. But the carbon-carbon bond length is 139 picometer. Okay, the carbon-carbon bond length is 139 picometer, and that is the 139 is in between 132 and 154. So molecular theory explain the bond length 139 picometer. Okay, so we know about the valence bond theory. Valence bond theory explain the two possibilities of benzene. But in MO theory, molecular orbital theory, they suggested that the electrons in the 6 carbon atom is delocalized. The pi bond is delocalized. Okay, let's check what happens in the case of benzene. According to VB theory, in benzene, the carbon atoms are sp2 hybridized. Okay, according to VB theory, the carbon atoms in benzene are in sp2 hybridized. All the carbon atoms are sp2 hybridized. The carbon atoms are sp2 hybridized. sp2 hybridization. In sp2 hybridization, one s orbital and 2 p orbital undergoing hybridization, and the third unhybridized orbital which contains one electron. Okay, let's draw the structure of benzene according to the VB theory, valence bond theory. All the carbon atoms which contains hydrogen, one hydrogen. Okay, one hydrogen atoms, and it is sp2 hybridized, and each of these carbon sp2 hybridized carbon atom having one unhybridized p orbital, one unhybridized p orbital. Okay, for convenience, let's draw like this. For our convenience, we draw the structure like this. Hydrogen atoms are condensed. Okay, hydrogen atoms are condensed. Say unhybridized p orbital, dumbbell in shape. And also let's number the carbon atoms. Number the carbon atom 1, 2, 3, 4, 5, 6. Okay, and these orbitals which are containing one electron. The orbitals which are containing one electron. And lateral overlapping between 1 and 2. The other possibility is lateral overlapping between 3 and 4. And the other possibility is between 5 and 6. What we get? We get the structure like this. Okay, all the 6 carbon atoms are same. That's why we get a hexagon. Then first and second double bond comes here. 3 and 4 the double bond comes here. And 5 and 6 the double bond comes here. That is one possibility. Okay, that is the one possibility, first possibility. And the second possibility is, the second possibility of structure of benzene is, again we consider the 6 carbon atom which contains hydrogen. Okay, that is we condensed. Also unhybridized p orbital. Unhybridized p orbital which contains one electron. Okay, each p orbital contains one electron. Also we number 1, 2, 3, 4, 5, 6. Then each orbital contains one electron. Each unhybridized p orbital contains one electron. Here the pi bond formation possibilities between 2 and 3. Okay, 2 and 3. Then 4 and 5. Here 1 and 2, 3, 4, 5, 6. Here the possibility 2 and 3, 4 and 5. Similarly 1 and 6. The possibility of pi bond formation 1 and 6. We get the structure. The structure of benzene is like that. Okay. This is the second structure. Okay, that means the electron, the possibilities are pi bond formation between 1 and 2, 1 and 2, 3 and 4, 5 and 6, we get one structure. The other possibility 2 and 3, 4 and 5, 1, 6 or 6, 1. Two possibilities are proposed by valence bond theory. But X-ray diffraction study shows that there is no single bond and a double bond in the benzene. Okay, as I already told you, if a single bond is present in the benzene, we get the bond length value 154 picometer. Okay, if there is CC bond, it is 154 picometer. If there is double bond, 132 picometer. In some textbook 133, no problem. 133 and 132 is nearly same value. In benzene, X-ray diffraction study shows that in benzene the bond length is 139 picometer. That is, the bond length is in between the double bond and single bond. And that is explained by AMO theory, molecular orbital theory. Hope you understand the possibilities. This is one possibility, this one is the second possibility. Okay. Then we discuss the resonance stabilization. Okay, it is a resonance. So benzene has many resonance possibilities, and these two, okay, the two important K-goal structure contribute more. Two structure is contributed more into the resonance hybrid. And we can write that benzene has a resonance hybrid, or here the bond between 1, 2, 3, 4 and 5, 6. Here the bond between the pi bond between 3, 4, 5, 6. 2, 3, 4, 5, 1, 6 or 6, 1. And the resonance hybrid is, we put a circle. Either we draw a circle or a dotted circle. That's very important. Okay. This is resonance hybrid. These two are resonance structures or canonical structures of benzene. That's a two main contributing structure to the resonance. And this is either you draw a circle or you draw a dotted circle. Are you clear? Okay. And the MO theory explanation. MO theory explanation of the bond length 139 picometer is benzene ring. It is a hexagonal ring. 6 carbon atom. All the carbon atoms are sp2 hybridized, which contains 1 electron. All the p orbitals which contains electrons, and these electrons are resonate. Okay, the electron cloud is resonate. The electron cloud is resonate through the 6 carbon atom, and we get 1 electron cloud in the above the plane. So that's why we can draw like this. Okay, one electron cloud in the above the plane, and similarly the other cloud in the below the plane, as like a sandwich. Okay, so in what there is a limitation, you can see this in the textbook. One electron cloud above the plane, one electron cloud below the plane, and that is the structure of benzenes. The MO theory explains the structure. The bond length is in between, carbon-carbon bond length is 139 picometer. Okay. MO theory easily explain the bond length 139 picometer. Why? The 6 electrons are resonating, delocalized. 6 electrons are delocalized through the ring. Okay, delocalized through the ring. So in a hexagon plane, the plane also contains 6 hydrogen. You remember that? Okay, the plane which contains 6 carbon atom and 6 hydrogen atom. One electron cloud above the plane, one electron cloud below the plane. It is like a sandwich. Okay, we take a bun and chop it, and we make a sandwich. So this structure is similar to a sandwich, and easily explain the bond length 139 picometer. Okay. However, we use these two Kekulé structure to explain the mechanism. Okay, to explain the mechanism of reactions of benzene, we use these two Kekulé structures, resonance structures, and this one is the resonance hybrid. Are you clear? Yes. Next we discuss the preparation of benzene. 3 methods, and some methods we already discussed. First one is from ethyl, preparation of benzene. First method from ethyl. Cyclic trimerization. Okay, already we discussed cyclic trimerization of ethyl. Okay. 3 moles of CH, triple bond of CH, is passing through red hot iron tube. At 883 Kelvin, we get benzene. Okay. You just refer the reactions of alkynes. Already we discussed. That's the first method. And second method is from benzoic acid, carboxylic acid. Decarboxylation of benzoic acid. Decarboxylation of benzoic acid. Decarboxylation is studied in the preparation of alkenes. So here also we can use the decarboxylation. Sodium salt of benzoic acid, or simply benzoic acid, is treated with soda lime. What is soda lime? Calcium oxide plus NaOH. Heated with the soda lime. Decarboxylation. This COO is removed and hydrogen is attached to the benzene ring. We get benzene. Or you can write benzene. And the byproduct is 2 sodium, carbon, 2 oxygen from here, 1 oxygen is here. The byproduct is Na2CO3. Okay, you refer preparation of alkane, decarboxylation of carboxylic acid. Same method, instead of R group, in the case of alkane we take alkyl group. Here we take benzoic acid. Okay, so that is the second method. And the third method is from phenol. Okay, third method is from the phenol. Phenol is treated with a zinc or distilled with the zinc, we get benzene. Third method is from phenol. A very simple reaction. This is a phenol, benzene ring and OH group. It is phenol. It is heated with the zinc or treated with the zinc. Okay. Then the oxygen taken by the zinc and we get the benzene. We get the benzene plus zinc oxide. Okay, these three methods is very important in the preparation of benzene. Substituted benzene we can prepare by some other reactions. We will discuss later. Okay, these three methods are very important in the preparation of benzene. Okay, first cyclic trimerization, second one is decarboxylation of benzoic acid, third one is from the phenol. Phenol is heated with the zinc. Zinc dust or zinc, we get benzene. So in the next section we will discuss the aromaticity and the properties, physical and chemical properties of aromatic compound or arenes, especially benzene. Okay, thank you.